we're continuing here with solving trigonometric equations, but we're going to change directions or instructions a bit. In these next few questions, we're going to be asked to find all solutions to a trigonometric equation. Now, so far we've been finding solutions that only lie between 0 and 2 pi. But when we open it up for all solutions, then there's an infinite number of solutions to most trigonometric equations. And it's because of the cyclic nature of these trig functions. That is, every time we make a rotation around the unit circle, we start repeating our positions on the unit circle, so the sine and cosine values keep repeating. So for instance, the sine of 0, well, let's use cosine. The cosine of 0 is 1, but so is the cosine of 2 pi, and so is the cosine of 4 pi, and so is the cosine of 6 pi. As far as that goes, so is the cosine of negative 2 pi, because when we move that amount along the unit circle, we end up in the very same position of where the angle 0 stops. So that's why I said what I've done here is we're finding the infinitude of solutions. In other words, we're going to have an infinite number of solutions. And so in these cases, it requires that we use formulas to indicate. So it requires the answer be in formula form. Otherwise, I mean, we can't list an infinite number of numbers, can we? So what we're going to do is list a formula that tells us how all those solutions look. Now, let's start with, not with solving anything, let's just start with the idea that if we consider the cosine of pi over 4. Now, we know that the cosine of pi over 4 is the square root of 2 over 2. We ought to be pretty comfortable with that. And of course, let's look at this picture over here of the unit circle. When we draw a unit circle, of course, the angle pi over 4 is roughly right there. And so the cosine of that angle is the first coordinate, and that's how we know, of course, that's where pi over 4 ends up, isn't it? Now, here's the issue, though. If we look at the cosine of whatever pi over 4 plus 2 pi is, that's also the square root of 2 over 2. Why do I say that? Here's the angle pi over 4. Now, if we take that angle pi over 4 and we add 2 pi to it, how far is it around the circle? It's 2 pi, a unit circle. It's 2 pi units, isn't it? So if we start at this angle of pi over 4 and we add 2 pi, we're right back to the same position. So this is also where pi over 4 plus 2 pi ends. Now, keeping that in mind, if we added, let's do this. Let's take pi over 4 and add 4 pi. Now, 4 pi is 2 of these 2 pi's, isn't it? And so what would be happening is that we would be going 2 more rotations. Let's say here's where pi over 4 is. Well, we're going to add 2 pi, which would put us back here, and then we're going to add another 2 pi. That gets us to 4 pi, which puts us in the same position. So the cosine of pi over 4 plus 4 pi is also the square root of 2 over 2. And you can imagine this is going to continue, isn't it? The cosine of pi over 4 plus 6 pi. We're just making one more revolution. And that's going to also be the square root of 2 over 2. And if we look closely at this, we could say, well, the cosine of pi over 4 plus 2 pi times some integer. See, like if k was 1, we would just have 2 pi. If k is 2, we would have 4 pi. If k is 3, we would have 6 pi. So k is an integer, just making sure that we go around 2 pi more units each time. So that's also going to be the square root of 2 over 2. That kind of leads us to, as I mentioned, we'd have pi over 4 plus 4 pi would also be in that position. Pi over 4 plus 6 pi would be in that same position. Pi over 4 plus 8 pi. We have to have increments of 2 pi, don't we? So here we're assuming k is an integer. Now, we have to also make sense out, of course, k could be 0, and if that were the case, it would just be pi over 4 plus 0, which is pi over 4. Now, it doesn't say k has to be a positive integer, because imagine this. Imagine we start where pi over 4 is, okay? Now, here's where the angle pi over 4 leads us. And we know the cosine of that angle being the first coordinate of that point that I've just put down is the square root of 2 over 2. Well, if that's pi over 4, if I start at that position and I go 2 pi units in the negative direction, see, 2 pi units in the negative direction, I'm still in that same place, aren't I? So that would be, I'm cramped in there, that would be pi over 4 plus a negative 2 pi. And we would most likely write that as pi over 4 minus 2 pi would put us in the same position. But we could go 4 pi in a negative direction. See, we could say, okay, well, why don't we go around twice in a negative direction? So we start at pi over 4, and we say, okay, go a negative 2 pi, and then go another negative 2 pi, and it still puts us in that same position. Well, this is pi over 4 minus 4 pi, okay, which we could say is pi over, plus negative 2 pi, but which is pi over 4 minus 4 pi. We could say it's minus 2 pi times the number 2. That's negative 4 pi, isn't it? See, up here we could say that this is pi over 4, and it's probably better to do it this way, plus 2 pi times a negative 1. See, I'm thinking down here we could write it as pi over 4 plus 2 pi times a negative 2. And so we can use integers that are positive or negative. Up here, this was just pi over 4 plus 2 pi times 0. I'm referring to the angle in here. And in this case, this is pi over 4 plus 2 pi times the integer 1. I'm referring to the angle in here. And of course, this is pi over 4 plus 2 pi times 2. That's plus 4 pi, again, the angle in there. Pi over 4 plus 2 pi times 3, well, that's the angle in there. And that's the impetus or the motivation for the way we would write this inside. And we've seen down here that that integer could also be, that k could be a negative 1 or a negative 2 or a negative 3. Okay, well that's the idea of what we're going to be doing. Let's solve an equation now where we have an infinite number of solutions and the way we'll write the equation for the infinite number of solutions. So here's our problem. We're to solve the equation cosine of theta equal negative square root of 2 over 2. And notice here it doesn't say over the interval from 0 to 2 pi. It doesn't say that. It just says solve the equation. Now, a part you see here, it says give a general formula or formulas, and a lot of them will be more than one formula, for all solutions. And so that's the idea that we're going to actually show how we determine all of the infinitude of solutions. And then after we do that, it says this, and not in this way. You see what it says. Then find the solutions for k equal negative 1, 0, 1, and 2. Now, k is part of the equation or equations that we're going to have, just as we saw on the previous page. And so we're going to be finding, in this case, 4 specific solutions out of the, or maybe more, of k used in every equation. So we're going to find some specific solutions based on those k values after we have the formula for all of the solutions. Okay, so here's the way we go about doing this. And when I say solution here, I'm referring to the solution to the problem. Now, cosine, there's not really a whole lot to do in terms of solving this equation. It's already solved for cosine of theta. So what I'm going to do here is I'm going to look at what angles will create that cosine value. And so I'm just referring to my unit circle over here, just to, that's kind of the way I remember all of this, okay? Now, negative square root of 2 over 2, oh, well, that's going to be in a position about like this, well, the angle is, I'm sorry, I'm mumbling here. Negative square root of 2 over 2, we recognize square root of 2 over 2 as something, and it has to do with pi over 4s, doesn't it? And so I can think, oh, well, in this position, I'm going to have a cosine value that's negative, and that's going to have something to do with pi over 4, isn't it? In fact, this angle, okay, if we think about the angle from here to here, this angle is, in fact, 3 pi over 4. But also in the third quadrant, we have a matching first coordinate. See, this would be the same first coordinate, wouldn't it? And so the angle that we get here would also have a cosine value of negative square root of 2 over 2. Sine value is different, but the cosine value is the same. And so that's the angle that we're referring to right here, and that will be 5 pi over 4. Well, as we discussed a moment ago then, the formulas, okay, we've actually got two formulas here. And the first has to do with the solution 3 pi over 4. So here's what we actually do. We find all the solutions to the equation in the first revolution, that is between 0 and 2 pi. And so we write down that one of those solutions, 3 pi over 4, and we'll write down the other solution, 5 pi over 4. Now let's concentrate on 3 pi over 4. The issue is this: if we start at 3 pi over 4 and we add or subtract multiples of 2 pi, then we'll be in the very same position, and the cosine of 3 pi over 4 plus 2 pi times some integer value is still going to be negative square root of 2 over 2. So this is one of the two formulas. The second of the two formulas would be, say, let's start at the angle 5 pi over 4, and let's add integer multiples of 2 pi. That means we can add 2 pi or 4 pi or 6 pi to that position. We'd be right back where 5 pi over 4 is. Or we could, if case negative, we could have negative 5 pi over 4 minus 2 pi. See, we're going in the opposite direction, but we're still in the same position. So this is really together, these two pieces together are part A. Okay, it takes two formulas to generate all of the solutions to this equation. Now, part B says, okay, let's consider these k values. K equals 0, negative 1 first, isn't it? 0, 1, and 2. And so here's the idea behind this. When k is negative 1, then the first formula says 3 pi over 4 plus 2 pi times a negative 1. And the second formula says 5 pi over 4 plus 2 pi times a negative 1. That's just making k negative 1. Well, what value is this? Okay, well, this value is 3 pi over 4 minus 2 pi. And of course, if I get a common denominator, this is 3 pi over 4 minus 8 pi over 4. And so this ends up being negative 5 pi over 4. So that is a solution. Remember, we have an infinite number of solutions. That's a specific solution, and that comes from the formula when k is equal to negative 1. Oh, but what about the second formula? Well, that would give us 5 pi over 4 minus 2 pi, which of course is the same thing as 5 pi over 4 minus 8 pi over 4. Just getting a common denominator, and of course that's negative 3 pi over 4. Now, if we let k be equal to 0, then we would put 0 into each of those formulas for the k value, and so we'd have 3 pi over 4 plus 2 pi times 0, which of course 2 pi times 0 is just 0, so that'd be 3 pi over 4. That's the very first one we found, wasn't it? And likewise, 5 pi over 4 plus 2 pi times our k value of 0 is simply 5 pi over 4. Then if we let k be equal to 1, we'll then see what we would get. Our first formula would be 3 pi over 4 plus 2 pi times 1. Well, 2 pi times 1 is just 2 pi, so this would be 3 pi over 4 plus 2 pi, which is 8 pi over 4, and so that would be 11 pi over 4. And likewise, if we had the second formula, 5 pi over 4, with a k value of 1, it would be 2 pi times 1. And that ends up being 5 pi over 4 plus 2 pi, but 2 pi I'm writing as 8 pi over 4, so I can add those together, and of course that's 13. Up here, I just saw that's 11 pi over 4, pardon me. And 5 pi plus 8 pi is 13 pi, so here we have 13 pi over 4. Oh, and I'm running out of room, aren't I? In the case of, let me come way back up here. In the case when we let k be equal to 2, then the first formula is going to look like 3 pi over 4 plus 2 pi times our k value of 2. And of course that's 3 pi over 4 plus 4 pi. Now I need to get a common denominator, which is going to be 4. So this is 3 pi over 4 plus 16 pi over 4. And you see that that's 19 pi over 4. Now that's just the first formula. The second formula is 5 pi over 4 plus 2 pi times 2. And I'm going to kind of jump a little bit ahead. That's 5 pi over 4 plus 4 pi, which is the same as 16 pi over 4. And so when we add those together, we get certainly 21 pi over 4. So we have what? We have this solution, this solution, this solution, this solution, this solution, this solution, and here. Because we had two equations. I mean, that was just for 4 values of k. And there's an infinite number of integers, and so again, there's an infinite number of solutions. It just depends on how many times we go around the unit circle in a positive way and or in a negative way. Okay. Well, on the next page, we're going to continue this thought, but we're going to have an equation that is a little different in looks. And so let's do that here. Excuse me, on the next page. Actually, I was a little bit ahead of myself when I made my statements on the previous page. This is going to be similar to what we just did. Solve the equation 2 sine theta minus 1 equals 0. Give a general formula or formulas for all solutions. The key is all solutions. Whenever we say all solutions, we know we're talking about an infinite number, and it requires a formula generally to show that infinite number or formulas. And then, like before, then find the solutions for k equals 0, 1, and 2. Okay, I think before it was k equal negative 1, 0, 1, and 2. This time just 0, 1, and 2. So the first thing we go about is we start solving like we normally did, okay? That is, we first go about finding the solutions thinking about a unit circle only, okay? So to do that, of course, we need to isolate the sine of theta itself, and so we add 1 to both sides first, and then we'll divide on both sides by 2, and we get the sine of theta is 1/2. So our next job then is to figure out what angles in one single revolution give us a sine value of 1/2. And of course, here's where 1/2 is, and we've discussed this before. So we're talking about an angle like that, because the second coordinate would be 1/2 there. Likewise, though, there's an angle over here that has a second value along the unit circle. The second coordinate, there's also 1/2, isn't it? And then we need to have some method that we can remember that this angle is pi over 6, and the angle that we're showing here, which of course gets to there in this fashion, here's in this fashion, is 5 pi over 6. Somehow or another, we've got to remember that, okay? I remember that this distance, this angle is pi over 6, And where I'm going to is pi. So I take pi and back off by pi over 6. And pi, of course, is 6 pi over 6. So that's the way I remember it. Okay, now from those two angles, we create our formulas. Okay, and it is formulas in this case again. So I think about the angle pi over 6 and recognize that if I add multiples of 2 pi to that angle, I will always end up in that same terminal position, that same position as pi over 6. And likewise, if I think about the angle 5 pi over 6, I can add multiples of 2 pi. They can be positive multiples of 2 pi or negative multiples of 2 pi. But regardless, then for any integer value k, positive or negative or 0, we will come up with another solution. So there are our two formulas. Those help us generate every single infinitude of solutions that exist. Now I'm going through here and I'm thinking, okay, let's look specifically when k is 0. And specifically when k is 0, we get pi over 6 plus 2 pi times 0, of course, which is just pi over 6. And of course, in the second case, we get 5 pi over 6 plus 2 pi times 0, which is just the same as adding 0, which is 5 pi over 6. So when k is 0, we have those first two that happened in the first rotation. Now, if k were equal to 1, we would have pi over 6 plus 2 pi times 1. And of course, when we add those together, we need a common denominator. And so I'm going to write 2 pi as 12 pi over 6. You can verify that, of course. And of course, that's pi plus 12 pi is 13 pi over 6. Now, if I use the second formula, that would be 5 pi over 6 plus 2 pi times 1. See, k is 1. But just as I did before, I'm going to write 2 pi in sixths so I can actually add these together. So I have 5 pi over 6, and 2 pi I'm actually going to write as 12 pi over 6 so that I can add those together. And you see, of course, that gives me 17 pi over 6. Now, on the other hand, if k was equal to 2, we might actually start seeing a pattern here. We might see a pattern. And I'll illustrate that pattern. Just be careful, of course. I'll illustrate that pattern in a moment. If k is 2, then we have pi over 6 plus 2 pi times 2, from the formula up here. And of course, 2 pi times 2 is just 4 pi. So this is pi over 6 plus 4 pi. And now I go about saying, well, I need a common denominator so I can add those together. And so I take 4 pi and multiply it by 6 over 6, and I get 24 pi over 6. And when I add pi and 24 pi, of course, I get 25 pi, so this is 25 pi over 6. Now, similarly for the second equation, I would have 5 pi over 6 plus 2 pi times 2, which of course is 4 pi. And then I'd write that 4 pi in a fashion so that I had a denominator of 6. And that ends up being 24 pi over 6. And so when I combine those, I end up with a 29 pi over 6. 5 pi plus 24 pi is 29 pi. And look, let's just notice, look at when we move from here to here, we've got 12 pi more on top, don't we? And then we move to here, 13 pi plus 12 pi more is 25 pi. Let's see what happens here. We move from 5 pi over 6 to 17 pi over 6. Well, 5 pi to 12 pi, 17 pi is 12 pi more, isn't it? And 17 pi to 29 pi is 12 pi more. So there is a little bit of a pattern that we might be able to deal with. But as we write these down for all of the solutions, I'm just starting at the top. We would have pi over 6, and the next size would be 5 pi over 6. And then the next size, here I am right here, would be 13 pi over 6. Now these are just the particular ones that we're getting because k was 0, 1, and 2. And then of course we have a 17 pi over 6. and then a 25 pi over 6, and finally a 29 pi over 6. And there's a whole lot more. There's an infinite number of them. But at least we've written the ones that go with k equals 0 and 1 and 2. A total of six solutions. Okay, well, we'll continue our discussion on the next page. Okay, we finally run into something that's different. It's some of the components are the same as what we've just been doing. It says solve the equation sine of 3 theta equal 1/2. Give a formula for all solutions, then find the solutions for k equals 0, 1, and 2. Now, it is obviously sounds like the same, and it is the same directions as the problems that we've done just recently. But here is a big difference. We're not any longer taking just the sine of theta. This is the first time this has happened in all of the examples we've seen so far. We've had tangent of theta, cosecant of theta, sine of theta, cosine of theta. We've never had the sine or cosine of a number times theta. So that's what makes this different. If we've got to pause, that's what makes this different. Well, we almost have to ignore that fact. Okay, we almost have to ignore that fact. And let's just imagine, just so that we can discuss this, okay? So it will look like other things that we've done. Let's replace 3 theta, what we're taking the sine of, with another angle name. Now, how about just alpha? Okay, just alpha. So in that case, we're being asked to find the solution to the sine of alpha is equal to 1/2. That's what we're being asked to do. Well, that shouldn't be too difficult, okay? So how do we deal with that? Well, we come and we draw ourselves a unit circle, and maybe we have some of these things memorized. That's not a very pretty circle, is it? But where the sine of an angle that gives us a result of 1/2, remember the sine. So here's where 1/2 is, because this is 1. We just went through this, didn't we? So we've got an angle here, and we've got an angle here. Now this angle is pi over 6, and this angle is 5 pi over 6. So I didn't do a very good job previously, and I'm sitting back and looking at that. You know, I should have said previously that for our solutions, our formulas, they were formulas for the angle theta, weren't they? Well, here's what we've got, okay, for our formulas. We've got 2 formulas that we're going to deal with here. And one of them is for the angle theta. Sine of what is 1/2? Sine of pi over 6 is 1/2. So our alpha angle could be pi over 6 or plus 2 pi times k, integer multiples of 2 pi added to it. Likewise, our alpha could have been 5 pi over 6 plus 2 pi k. Okay, so that looks similar, except I've just got a different name for my angle. But here's the rub. Here's the difference now. What we were asked to do is solve the equation sine of 3 theta is equal to 1/2. And I temporarily called 3 theta alpha. So what I really have here is one formula, the first formula. If I call this one the first one and this is the second one, the first formula, if I go back and put in 3 theta for the alpha that I temporarily had there, then I've got 3 theta is pi over 6 plus 2 pi k. So that ends up being the first formula, and the second formula ends up being 3 theta is equal to 5 pi over 6 plus 2 pi times k. Now the problem with these formulas is it tells us what 3 theta is equal to. And of course, we're trying to solve for theta. See, we're trying to solve for the angle theta. That was our original issue, wasn't it? Solve for theta. So we've got to take each of those particular equations equation 1, and we've got to solve it for theta. So instead of having 3 theta on the left side, we need theta on the left side. And so here's the way I would do that. I would say, why don't we multiply this left side by 1/3? Because 1/3 times 3 theta is certainly just theta, isn't it? So we'll get our theta. Now, if I multiply the left side by 1/3, I'm going to multiply the right side by 1/3. Now, when I multiply on the right side by 1/3, I have 1/3 times pi over 6. Well, that's 1 times pi over 3 times 6. That's pi over 18, isn't it? And then when I look at the next multiplication, I've got 1/3 times 2 pi k. And isn't that nothing more than 2 pi k over 3? So equation 1, when solved for theta, looks like the equation that we see here. Okay, so this is one of the two formulas. Now, in the other case, the second formula starts out as 3 theta is equal to 5 pi over 6 plus 2 pi k. And when I multiply on the left by 1/3 so that I'm solving for theta itself, I've got to be sure to multiply on the right by 1/3. And of course, 1/3 times 3 theta is theta. That's the whole reason we did that. 1/3 times 5 pi over 6 is 5 pi over 18, plus 1/3 times 2 pi k is 2 pi k divided by 3. So this is our second formula. Now, when k is 0, we just take each of those formulas and replace k with 0, and in that case, the first formula gives us theta is equal to, whoops, this was an 18. Did you catch me way back up here? 1/3 times pi over 6 is 1 times pi over 3 times 6. That was an 18, wasn't it? But it is correct that we have a 3 here. So if k is 0, then this fraction becomes 2 pi times 0 over 3, or just 0 over 3, which is 0. So here we get pi over 18 only. And then the other theta value that we would get is when we use this formula and a k value of 0, and in that case we would simply get 5 pi over 18. So there's two solutions, the two solutions we get when k is 0. Now, when we let k be equal to 1, the first formula is pi over 18 plus 2 pi times 1, which is just 2 pi over 3. Now, this one requires a little bit more work because we ought to be able to add those two fractions together, shouldn't we? And so we're going to multiply the second fraction by 6 over 6 to get a common denominator of 18. And so we'll have pi over 18 plus 12 pi over 18. That's the same thing as 2 pi over 3. And you see, of course, when we add those together, we get 13 pi divided by 18. Now, that's just for the first formula. For the second formula, we would have theta is equal to 5 pi over 18 plus 2 pi times 1 over 3. And just as we saw a moment ago, we will get a common denominator so we can add these two together, and that would be 18, and so we'll write 2 pi over 3 again as 12 pi over 18. And so the result here, of course, is 17 pi over 18. And if k is equal to 2, we just go through this process again. Theta would be, for the first formula, pi over 18 plus, I'm looking at the formula right here, 2 pi times k, which is 2, that's 4 pi over 3. Now I need a common denominator, which is going to be 18, and so this 4 pi over 3 I will write as 24 pi over 18. And that ends up being, of course, 25 pi. over 18. Now that's for the first formula. The second formula would give us theta is 5 pi over 18 plus 4 pi over 3 in a similar fashion. And that's 5 pi over 18 plus 24 pi over 18, which of course is 29 pi over 18. So using those 3k values, we get 6 solutions, 3 for each formula. So there's 2 of the solutions. Here is an additional solution, an additional solution, an additional, and an additional. So that's the approach we take there, is we can temporarily replace that multiple angle, 3 theta, that multiple angle with a single angle like alpha, and go about our business and then resubstitute. Now this time, we don't have a number times theta, we have theta divided by a number. We're to solve, as you see, the cosine of theta over 2 equal the square root of 2 over 2. And it says give a formula, and probably there's going to be 2 or more. Give a formula for all of the solutions, and then find the specific solutions that go with the values of k equals 0, 1, and 2. So, as we did before, the problem that we have is that our equation looks funny. So our first inclination, I hope, is let's replace theta over 2 with some other angle name like alpha. So in the place of theta over 2, I'm going to put alpha. And so that means it looks like what we're solving is the cosine of alpha is equal to the square root of 2 over 2. Now, there's going to be 2 angles in the very first revolution that do that, okay? And we ought to be getting to where we recognize what angles have a cosine value of the square root of 2 over 2. And that would be here, which is pi over 4. Now, it could also be down here because we could have that's fine. Now, what angle is that? Well, we're thinking of positive angles to get started, so we're coming clear around this way. And that angle is 7 pi over 4. So we set up, now this is where we're going to set up those formulas. We're going to start with setting up the formulas by using those specific angles. And so we could say, okay, well, alpha is pi over 4 plus any integer multiple of 2 pi. Or, when we're using the other angle, alpha could be 7 pi over 4 plus any integer multiple of 2 pi. The problem is, as we just saw a moment ago, we're really needing a value for theta, not for alpha. So we come back in here, we'll do these kind of side by side, but one at a time, replacing alpha with theta over 2. So the first formula becomes theta over 2 is equal to pi over 4 plus 2 pi k. And just so I have room, the second formula over here becomes, I'm replacing our alpha with originally what it is, and that's theta over 2. So instead of alpha, theta over 2 is equal to 7 pi over 4 plus 2 pi k. Now, I'm needing to solve for alpha. See, that's what solve for theta. I need it to say theta is equal to. That's what we're trying to do. What values of theta make the equation true? And so I'm noticing that if I multiply on the left side by a 2, I'll end up with theta. So, of course, I have to multiply on the right side by 2 as well. On the left side, of course, I have theta. That was by design. And then notice when I multiply 2 and pi over 4, that gives me 2 pi over 4, which simplifies to pi over 2, doesn't it? So when I do this multiplication, I get a pi over 2, and then I'm going to multiply that 2 pi with the second term, and 2 times 2 pi k is 4 pi k, isn't it? And so there is one of the 2 formulas. We're going to do the same thing over here. for this formula. We're going to multiply both sides by 2. Now again, when I multiply theta over 2 by 2, I get theta. And when I multiply over here in my margin, if you will, 2 times pi over 4 is 2 pi over 4, which ends up just being pi over 2, doesn't it? Whoops, except that was a 7 pi over 4. That's my bad. That was a 7 pi over 4, wasn't it? I couldn't read my own writing. So it's 2 times 7 pi over 4, which ends up being 14 pi over 4, but that reduces to 7 pi over 2. So when I do that first multiplication, I get 7 pi divided by 2, and then 2 times 2 pi k is 4 pi k. So there are my two formulas. And now I'm worried about when k is 0. Well, when k is 0, the first formula gives me theta is equal to pi over 2. And the second formula gives me theta is equal to 7 pi over 2. K being 0 is simple, isn't it? When k is equal to 1, I might have to work harder. The first formula gives me theta is equal to pi over 2 plus 4 pi times 1. And so when I'm looking at that, let's see, that I need a common denominator, so that's pi over 2 plus 8 pi over 2. And of course that calculates to 9 pi over 2. Now the second formula is theta is 7 pi over 2 plus 4 pi times k, and since k is 1, that's just plus 4 pi. So we go through the process again. This is 7 pi over 2 plus an 8 pi over 2, just so I can add those together. And of course that gives a 15 pi over 2. And then of course if k is equal to 2, my first formula gives me theta is equal to pi over 2 plus 4 pi times 2, which is 8 pi. And when I go to get a common denominator, multiply 8 pi by 2 over 2, I get 16 pi over 2. So that ends up being, what, a 17 pi over 2? When I use the second formula, I have 7 pi over 2 plus 8 pi, just as we've been doing. And so that's 7 pi over 2 plus 16 pi over 2, which ends up being 23 pi over 2. So I have 1, 2, 3, 4, 5, 6 solutions again, don't I? For those k values. There's an infinite number of solutions. Well, in this talk, I want to do one more, and because it looks different, and we might try to do the wrong thing. Okay, then that's really what I'm concerned about. We might try to do the wrong thing. So let me start that on the next page. Solve the equation cosecant of 3 theta over 2 equal negative 2 over the interval from 0 to 2 pi, not including 2 pi. So this is almost like the kind of equations that we started with early on, except we don't have theta here, we have the cosecant of 3 theta over 2. Now, let me tell you what we need to do here. And the issue you'll see maybe in a moment. Let's find a formula for all solutions. Find a formula or formulas. And then use different k values to find, out of all those infinite solutions, to find the solutions that are between 0 and 2 pi. And maybe this will come to light as we do it. So here actually I'm going to take out the middleman in this case. But well, let me, I'm sorry, I'm babbling. We're trying to solve cosecant of 3 theta over 2 is equal to -2. Well, the very first thing I'm going to do is write that in terms of functions that I'm used to. And I recognize cosecant is the same as 1 over sine. So this is 1 over the sine of 3 theta over 2 is equal to -2. And now, okay, let's move clear back over here. Now I'm going to multiply both sides by the sine of 3 theta over 2 so I don't have it in a denominator. And when I do that, I'll end up with 1 only on the left side and -2 times the sine of 3 theta over 2 on the right. And now I'm going to divide out the -2. And when I do, and I'm taking more than one step at this time, on the right side, when I divide out -2, I'll have the sine of 3 theta over 2. And on the left side, I'll have 1 divided by -2, which is -1/2. But I like my trig functions to be on the left, so that's what I've done here. Now previously, see now it looks more like, here's the issue, is we're asked to do this now back between 0 and 2 pi. But this looks like the kinds of problems we just got finished working on. And so again, what we're going to do is come up with a formula. Now previously, what I've done is I say, well, let's replace 3 theta over 2 with an alpha, and then let's go about our business. But I don't really need to go to that much trouble. I can just say, okay, it's 3 theta over 2 that I'm finding rather than alpha or rather than just theta. I'm finding what angle, when I take the sine of 3 theta over 2 to get a -1/2, what does 3 theta over 2 have to be? Now to get it -1/2, that means I'm down here someplace for a sine value, right? So I'm talking about an angle that is here, that has a second coordinate of -1/2, or an angle that's here, that has a second coordinate of -1/2. But remember, I'm going in this direction. And so this ends up being 7 pi over 6 in this position, and this ends up being 11 pi over 6 in this position. So equation one, instead of saying alpha is equal to 7 pi over 6 plus 2 pi k, I'm just going to say 3 theta over 2. See, I called that alpha before. 3 theta over 2 is equal to 7 pi over 6 plus 2 pi k. Now, as I go about and solve this for theta, I would multiply by 2 first. And when I did, I would get 3 theta is equal to 7 pi over 3, because 2 over 6 is 1 over 3, isn't it? It would just reduce. I'd get 14 over 6 and reduce it, but I'm going to multiply the 2 pi k with 2 as well, and that gives me 4 pi k. And now I'm going to go through and multiply by 1/3. And when I multiply the very first term over here, oh, let's just write it out. Well, 1/3 times theta gives me theta, times 3 theta gives me theta. 1/3 by the first term over here is 7 pi over 9, and 1/3 times 4 pi over k is 4 pi k over 3. Now, for the second equation, I would say instead of alpha over 2, I would say once again, 3 theta over 2 is our angle 11 pi over 6 plus 2 pi k. When I multiply on both sides by 2, I'll get 3 theta is equal to 11 pi over 3 plus 4 pi k. When I multiply on both sides by 1/3, I get theta is equal to 11 pi over 9 plus 4 pi k over 3. Now, those are the formulas. And here's the first question. if k is equal to 0, what thetas are those? Well, the first formula gives me theta is 7 pi over 9. And the second formula gives me 11 pi over 9. And so the question is, are those solutions between 0 and 2 pi? Well, how would we know that? Well, we're comparing, so here's really what we're comparing. Just think about this. 7 pi over 9 is the same thing as 7 over 9 times pi. So when we compare that to 2 pi, see, we're comparing the 7/9 and the 2. Is 7/9 smaller than 2? Of course it is. 7/9 is smaller than 1, isn't it? So that means that 7 pi over 9 is in fact less than 2 pi. It's between 0 and 2 pi. And likewise for 11 pi over 9. Since 11 over 9 is just a little bit bigger than 1, it's not 2, okay? Then both of those are values between 0 and 2 pi. So now let's try k equal 1. Well, when we try k equal 1, the first formula, okay, the first formula gives me 7 pi over 9, when k is 1, plus 4 pi over 3. So I'm looking at the formula there. Well, let's see. When I add those together, I'll have 7 pi over 9, but I've got to get a common denominator, so that's going to be 12 pi over 9, isn't it? Multiply numerator, denominator by 3. And that ends up being 19 pi over 9. Is that right? 19 pi over 9. Oh, 19 pi over 9 is bigger than 2 pi. 19 over 9 is bigger than 2, isn't it? So we got too big already. Let's check one more with the second formula, but it ought to be bigger yet. Okay, so with the second formula, if k is equal to 1, my theta would be 11 pi over 9 plus 4 pi times 1, which is just 4 pi divided by 3 then. And so when I add these together, I'd have 11 pi over 9, and here I'd write this as 12 pi over 3. Excuse me, over 9. Pardon me. Multiply numerator, denominator by 3. And that gives me 23 pi over 9. Well, 23 over 9 is bigger than 2. So this is bigger than 2 pi. And of course, I'm just getting bigger by adding more multiples of pi. And so I can really stop at this point. If you will, that's all there is, folks. 23 pi over 9 is not good. Now, those might have been good in a different problem, and then I try k equal 2 and still see if I have good values. But in this case, the solutions are 2. Theta is equal to 7 pi over 9, and theta is equal to 11 pi over 9. Both solve that equation, and they're between 0 and 2 pi. Although there's an infinite number of solutions, those are the only ones between 0 and 2 pi. Well, we've covered a lot of ground. We've looked at a lot of solving equations, problems, examples, and that's very important when you get into calculus to be able to solve trigonometric equations. So good luck on your homework.